Module 11, Risk Assessment and Mitigation Strategies, AI-integrated enhanced version. Welcome to Module 11, Risk Assessment and Mitigation Strategies. Every modification introduces uncertainty. Your ability to identify hazards, evaluate risk, and design layered controls determines whether that uncertainty becomes a managed risk or an incident waiting to happen. In this module, you'll practice structured hazard identification, apply the hierarchy of controls, and develop realistic mitigation plans for real-world change scenarios. The risk matrix helps prioritize which hazards demand engineering intervention versus procedural control. Choosing the right method means balancing depth with efficiency. A checklist might suffice for a label change, but a haze-op is essential for a piping reroute. Reflection. Prompt. Which method does your team use most often? And is it always the right one? 1. Hazard identification. Methods and tools. Concept. Effective risk management begins with identifying what could go wrong, why, and how. Method. What-if analysis. Purpose. Explore possible deviations. Typical use case. Early project or design change. Strength. Fast and flexible. Method. HAZOP. Purpose. Systematic study of parameters. Typical use case. Equipment process modification. Strength. Deep and structured. Method. Checklist review. Purpose. Compare with existing standards. Typical use case. Routine changes. Strength. Ensures compliance. Method. JSA. Job safety analysis. Purpose. Step-by-step hazard review. Typical use case. Fieldwork and maintenance. Strength. Practical and accessible. The risk matrix helps prioritize which hazards demand engineering intervention versus procedural control. 2. Evaluating risk, likelihood. X severity matrix. A structured matrix turns qualitative discussion into quantifiable judgment. Likelihood, severity, rare, minor, low, moderate, low, major, medium, severe, medium, catastrophic, high. Likelihood, severity, unlikely, minor, low, moderate, medium, major, medium, severe, high, catastrophic, high. Likelihood, severity, possible, minor, medium, moderate, medium, major, high, severe, high, catastrophic, critical. Likelihood, severity, likely, minor, medium, moderate, high, major, high, severe, critical, catastrophic, critical. Likelihood, severity, almost certain, minor, high, moderate, high, major, critical, severe, critical, catastrophic, extreme. Remember, PPE is your last line, not your first. Your goal is to eliminate or engineer out the hazard whenever possible. 3. Hierarchy of controls in practice. Level. 1. Elimination. Control type. Remove the hazard entirely. Example. Discontinue use of flammable solvent. Effectiveness. Highest level. 2. Substitution. Control type. Replace with safer material. Example. Use water-based cleaner. Effectiveness. High level. 3. Engineering controls. Control type. Isolate people from hazard. Example. Ventilation. Guardrails. Effectiveness. Medium level. 4. Administrative controls. Control type. Adjust work, process, training. Example. Permit to work system. Effectiveness. Low level. 5. PPE. Control type. Individual protection. Example. Gloves, respirators. Effectiveness. Lowest. New section. 4. Interactive risk reduction challenge scenario. You've evaluated a process as high risk, likely X severe, due to the use of a flammable solvent. Task. Actively reduce the risk using the hierarchy of controls. Options. 1. Elimination, substitution. Replace solvent with non-flammable alternative. Risk drops to low. 2. Engineering control. Install a closed ventilation system. Risk drops to medium. 3. Administrative PPE. Require permits and flame-resistant gloves. Risk remains high. AI feedback. Excellent. You reduced risk to an acceptable level by eliminating the hazard source. This is the most effective and sustainable form of risk control. Learning point. This exercise turns passive knowledge of the hierarchy into active design thinking, showing participants that their choices directly shift the risk level. 5. Documentation and follow-up controls. Every mitigation plan must be documented, verified, and closed. Hazard ID RA001, control type, engineering ventilation upgrade, responsible, maintenance, due date, 10, Novers, verification, HSE inspection, hazard ID RA002, control type, administrative, SOP update, responsible, operations, due date, 15 Nover verification, supervisor check, hazard ID RA003, control type, PPE, gloves for acid handling, responsible, procurement, due date, 20 Novi, verification, field audit. Documentation is what transforms decisions into institutional memory. Without records, controls lose their meaning. New addition, regulatory compliance gate activity. Add a mandatory regulatory compliance check before MoC closure. Scenario prompt, you're modifying a pressure relief valve. Which action ensures compliance with API 521? Options: A. Reviewed by engineer. B. Verified and documented compliance with API 521. C. Reviewed by legal department. Every MoC must pass through a compliance gate. Technical risk assessment is not complete without confirmation that all applicable standards, API, ASME, ISO, or GOST, are satisfied and documented. Rationale. This addition reinforces that risk management via technical plus regulatory control, ensuring that no modification bypasses industry standards. 6. Integrating risk assessment into MoC workflow. Flow. 1. Change proposed. 2. Hazard identified. 3. Risk ranked. 4. Mitigation applied with challenge. 5. Compliance verified. Regulatory gate. 6. Documentation completed. 7. Closure and feedback. MoC is a living workflow. Every approval step must confirm that risks are known, reduced, and compliant. Each review cycle improves your future performance. True risk maturity means learning not just from failure, but from prevention. 7. Continuous improvement and lessons. Learned phase. Plan. Action. Identify hazards and controls. Outcome. Prevention by design. Phase. Do. Action. Implement mitigation. Outcome. Safe execution. Phase. Check. Action. Evaluate effectiveness. Outcome. Continuous learning. Phase. Act. Action. Update standards. Outcome. Institutional resilience. You've now seen risk management not just as a matrix, but as an active decision process. You've practiced reducing risk interactively and ensuring compliance through formal gates. This is the mindset of a resilient organization. One that turns uncertainty into structured safety. Module 12. Post-implementation review and effectiveness. Check. AI-integrated. Welcome to Module 12. Post-implementation review and effectiveness check. A change is only successful if it continues to perform safely, reliably, and as intended, months after implementation. In this module, you will learn how to verify that controls, training, and procedures remain effective over time and ensure that no unintended consequences emerge. 1. Purpose of Post-Implementation Review, PIR. Definition. A post-implementation review, PIR, is a structured follow-up performed typically 3 to 6 months after a change is implemented. It validates that the modification achieved its intended outcome. No new hazards were introduced. All procedures, documents, and training remain effective. Objective. Performance verification. Focus area. Is the change working as planned? Output. Performance report. Objective. Safety validation. Focus area. Are safeguards effective? Output. Updated risk register. Objective. Compliance check. Focus area. Are standards maintained? Output. Compliance confirmation. Objective. Learning capture. Focus area. What went well, what failed? Output. Lessons learned record. A post-implementation review closes the feedback loop. Without it, organizations risk repeating the same design or process errors, only with new names. Timeline. At implementation, 0 month. Responsible. MoC owner. Focus. Ensure readiness and documentation. Deliverable. Startup checklist. Timeline. 3 months after. Responsible. HSE. Operations. Focus. Monitor real performance. Deliverable. Interim review report. Timeline. 6 months after. Responsible. MOC committee. Focus. Validate long-term effects. Deliverable. Final effectiveness review. Timeline. 12 months after. Optional. Responsible. Management. Focus. Continuous improvement. Deliverable. Lessons integrated into system. The most common weakness in MOC systems is the lack of structured follow-up. This timeline turns good intentions into scheduled accountability. 3. Verification of training, procedures and controls activity. Post-change effectiveness survey. Each follow-up should assess 3 dimensions. Dimension, training, verification method, field interviews, e-learning completion. Example. Question. Do operators understand the new alarm logic? Dimension, procedures, verification method, document review, SOP audit. Example question. Are new startup steps reflected in the current procedure? Dimension, controls, verification method, instrument calibration, system data. Example. Question. Is the interlock still functioning as designed? A change that works technically but fails in training or documentation is an incomplete change. Every MOC closure must verify competence and procedural accuracy. 4. Interactive scenario. The quiet drift. Scenario. A control valve was upgraded 6 months ago to improve energy efficiency. Since then, several operators have manually bypassed it due to slow response. Task. Identify what should trigger a post-implementation effectiveness check. Options. A. Wait for the annual audit. B. Initiate an immediate PIR to verify control logic and operator feedback. C. Assume it's minor and proceed with production. Correct. Operator workarounds often indicate hidden design or training weaknesses. An immediate review prevents normalization of deviation. 5. Effectiveness indicators. Dashboard. To evaluate whether the change truly delivered its goals. Indicator type. Performance. Metric example. Energy efficiency improvement, %. Source. Process data. Target. At least 5% gain. Indicator type. Safety. Metric example. 0 incidents or near misses. Source. HSE reports. Target. Maintain 0. Indicator type. Training. Metric example. Completion rate, %. Source. LMS. Training log. Target. At least 95%. Indicator type. Procedural compliance. Metric example. Deviations from standard procedures. Source. Audit findings. Target. No more than 2 per quarter. Indicator type. Reliability. Metric example. Equipment downtime. Hours per month. Source. Maintenance data. Target. No more than 10 hours. Metrics transform perception into proof. If you can't measure the change, you can't declare it successful. 6. Post-implementation effectiveness gate. Before the final MOC closure, a formal effectiveness gate must confirm. Check item. Training verified and documented. Status. Responsible. HR. HSE. Check item. SOPs updated and in circulation. Status. Responsible. Operations. Check item. Controls validated. Alarms. Interlocks. Status. Responsible. Engineering. Check item. No new hazards identified. Status. Responsible. Safety. Check item. Performance meets defined targets. Status. Responsible. MOC owner. Check item. Final review signed off. Status. Responsible. MOC. The effectiveness gate ensures that the change is not only implemented, it's sustainable. No MOC is complete until this gate is signed and archived. 7. PIR findings and MOC trigger. New section. Concept. PIR is not a substitute for PSSR, pre-startup safety review, nor is it a tool to legitimize undocumented changes. If a PIR identifies an unintended or uncontrolled modification, it must initiate a new MOC. Post-implementation reviews can reveal hidden risks or process drifts. But remember, if the change itself wasn't approved, your PIR just found a new change, not a lesson. Interactive activity. PIR findings classification. Scenario 1. The PIR reveals that operators created a new manual bypass not documented in the SOP. Task: classify the finding. A. Lessons learned. B. New MOC, retroactive. C. PSSR failure, correct. A bypass introduces a new operational mode. It's a process change, not a simple lesson. A new MOC must be opened to assess its risks and controls. Scenario 2. The PIR shows that the training schedule was delayed, but all staff were eventually trained. Task: classify the finding. A. Lessons learned, procedural. B. New MOC, correct. This issue affects procedural compliance, not process design. It's a lesson for administrative improvement, not a retroactive MOC. AI rationale. This distinction prevents retroactive MOC misuse. PIR evaluates effectiveness, while MOC manages change. Uncontrolled findings discovered in PIR must re-enter the MOC workflow for proper risk assessment. 8. Lessons learned and continuous improvement step. Identify. Action. Capture post-change findings. Purpose. Learn from real performance. Step. Analyze. Action. Compare expected versus actual outcomes. Purpose. Detect systemic issues. Step. Share. Action. Integrate into design and training. Purpose. Prevent recurrence. Step. Apply. Action. Update MOC database and standards. Purpose. Institutional learning. A mature organization does not close a change, it learns from it. Every review is an opportunity to strengthen the system. You've completed Module 12, Post-Implementation Review and Effectiveness Check. You now understand that change management doesn't end at implementation, it ends with verification. By performing structured PIRs, distinguishing them from PSSR, and converting findings into new MOCs when needed, you ensure your organization's change system remains proactive, compliant, and resilient. Module 13, Knowledge Transfer and Legacy Management, AI-Integrated. Welcome to Module 13, Knowledge Transfer and Legacy Management. In this final stage of the MOC lifecycle, we move beyond implementing change to preserving its rationale, protecting organizational memory, and preventing creeping change. Our goal is to ensure that the why, how, and who behind each change remain visible, traceable, and linked to your process safety information, PSI. 1. Purpose and scope. Objective: to ensure that all MOC-related knowledge, decisions, risk assessments, lessons learned, and procedural updates is retained and accessible across time, teams, and technologies. Focus area: creeping change prevention. Purpose: capture all minor modifications and avoid unrecorded drift. Output: change tracking log. Focus area: rationale preservation. Purpose: document decision logic and engineering justifications. Output: change rationale register. Focus area: legacy continuity. Purpose: protect organizational safety memory through structured transfer. Output: knowledge transfer plan. Focus area: PSI integration. Purpose: link historical data with current process safety documentation. Output: PSI integrity check. Knowledge transfer is not about keeping files, it's about keeping context. Each change tells a story. Our job is to make sure that story never gets lost. 2. Preventing creeping change definition. Creeping change refers to the slow, undocumented drift in operations, design, or procedures, often caused by routine workarounds or silent deviations. Source: operator habit. Example: manual override becomes routine. Preventive action: regular MOC log review. Source: maintenance change. Example: alternative spare part installed. Preventive action: engineering approval for substitution. Source: software patch. Example: control logic updated but undocumented. Preventive action: MOC trigger for software update. Creeping change begins where documentation ends. By tracing small deviations early, we prevent them from becoming systemic risks. 3. Maintaining accessible change. Rationale and historical logs. Core principle. Every e-MoC should leave a transparent trail, not just of what changed, but why it changed, and what risks were considered. Document type. Approved e-MoC packages, repository, e-MoC database, DMS, access rights, all departments, retention period, 10 years minimum. Document type. Risk assessments, HAZOP, what if, repository, HSE repository, access rights, HSE, engineering, retention period, asset lifetime. Document type. Training records, repository, LMS, HRAS, access rights, HR, supervisors, retention period, 5 years, plus. Document type. Lessons learned, repository, knowledge portal, access rights, all employees, retention period, permanent. When rationale is spread across folders and emails, it becomes invisible. Centralized digital archives make knowledge not only preserved, but usable. 4. Preparing for personnel turnover. Challenge. Expert retirement. Risk. Knowledge drain. Solution. Structured exit interviews and knowledge capture sessions. Challenge. Contractor rotation. Risk. Process awareness gaps. Solution. e-MoC-linked induction and retraining. Challenge. Digital migration. Risk. Loss of traceability. Solution. Data validation and controlled transfer. When people leave, knowledge should not leave with them. Knowledge continuity is safety continuity. 5. Strengthening organizational memory. Link to PSI integrity. New reinforcement. Formal integration of supplier and change knowledge into PSI. Often, e-MoC knowledge, especially supplier or specification changes, is not properly integrated into process safety information, PSI, causing future inconsistencies or safety gaps. Step. Supplier or material change. Action. Update SDS and material master list. Verification output. Revised PSI record. Step. Design or equipment update. Action. Update PNIDS drawings. Verification output. Controlled revision. Step. Operational or procedural change. Action. Update SOP and training material. Verification output. Updated PSI library. Step. Legacy change review. Action. Ensure e-MoC rationale aligns with current PSI. Verification output. PSI integrity check form. Every change that affects what we store, handle, or process affects PSI. If the information in PSI is outdated, your safety foundation is outdated too. 6. AI-driven knowledge continuity tools. Tool type. AI search engine. Purpose. Retrieve e-MoC records by topic or equipment ID. Application example. Show all e-MoCs related to relief valves. Tool type. Automated tagging. Purpose. Link similar incidents and learnings. Application example. Connects all compressor seal leaks across units. Tool type. Predictive insights. Purpose. Highlight recurrent weak spots. Application example. Flags repeat deviations in bypass logic. Tool type. AI mentorship library. Purpose. Capture expert decision making. Application example. Recorded engineering judgment sessions. Artificial intelligence doesn't replace experience, it preserves it. AI tools ensure that what one engineer learned, the next can apply instantly. Interactive exercise. Knowledge management plan development scenario. You are preparing for 2 senior engineers' retirement and must create a knowledge transfer plan for the last 5 e-MoCs involving process safety equipment. Task. Design a structured plan covering what data must be retained, where will it be stored, who is responsible for updates, how will successors access and review it. A good plan ensures traceability, an excellent plan ensures context. Remember, the meaning behind the data is as critical as the data itself. Section. Knowledge scope, example entry, change in safety valve set points. Section. Storage location. Example entry, central e-MoC database, plus PSI archive. Section. Owner. Example entry, engineering lead. Section. Transfer method. Example entry, AI recorded walkthrough session. Section. Validation cycle. Example. Entry. Annually or post-audit. 8. New addition. Knowledge retention trigger for new e-MoC. Concept. If during post-review or handover it is discovered that undocumented changes, gaps, or deviations exist, this must trigger a new MoC, not just a note in lessons learned. Interactive activity. Knowledge gap, MoC trigger. Scenario 1. During turnover, it's found that a minor control logic update from 2022 was never formally documented. Task, classify, A, lesson learned, B, new MoC required, C, administrative error. An undocumented logic change is a process modification. Even if it's historical, it must be formalized through a retroactive MoC. Scenario 2. Missing training records for one operator, but no process change occurred. Task, classify, A, lesson learned, B, new MoC, C, PSSR failure. Documentation gaps in PSI or MoC systems aren't clerical, they're safety issues. Retroactive MoCs ensure no undocumented risks persist in your process history. 9. Integration into continuous improvement loop. The final stage of knowledge and legacy management ensures that lessons learned are continuously fed back into the organization's systems, closing the MoC lifecycle loop. After every post-implementation review, PIR, the key findings, decisions, and rationale must be captured and recorded in the lessons learned database. This step guarantees that insights from past changes are accessible for future reference and organizational learning. Before initiating any new MoC, teams should retrieve and review similar historical cases using the AI Search or MoC portal. This enables better decision-making, prevents repeated mistakes, and supports knowledge-driven risk assessment. During internal or external audits, the organization must verify that all documentation and process safety information, PSI, remain current and consistent. Auditors and HSE teams use the compliance tracker to identify discrepancies and track corrective actions. As part of the annual management review, obsolete or redundant records must be purged, while critical data and process safety information are revalidated to ensure ongoing accuracy and integrity. This process is managed through a structured document control plan, ensuring that only valid, up-to-date information remains in the system. Legacy management completes the MoC lifecycle, feeding verified knowledge back into design, operations, and future change decisions. Continuous improvement is not an event. It's a living process that keeps your organization intelligent, adaptive, and safe.